Welcome to the session. Greeting of the day. We are on the talk of types of sensors from the last classes. We have seen in types of sensors we have already in the discussions of finding out the displacement sensors, position, some examples of potentiometers, Hall effect, capacitive sensors, strain gauges, all these things we have already on the discussions. In continuous with that, in this class we will talk about the force sensor. The next category we have seen about the displacements, positions, and now we are going to talk about the force measurements. This is also one of the which we have already seen in the category of strain gauge measurements, the displacement. Here also the same setup of sensor we are going to use. See, a spring balance is an example of the force sensors that we know. We are measuring putting the load over the spring and it's identifying. In others, we can also use the strain gauge load cell for the measurement of the load. How? See, this is the setup of a strain gauge measurement. We have taken an object which we want to measure the compression or tensile loads. Right. The change in the resistance is a measure of force applied. We know the actual resistance of the strain gauge. You have also seen in the previous classes about the strain gauge measurements. So when this strain gauge have some fixed calibrated resistance, when that resistance has been changed, that belongs to the maybe a compression load, that belongs to maybe a tensile load. That is what we have taken that strain gauge measurement and we have fixed it here. Okay? We have fixed it there. When a force or load is applied here, what happens there? It compresses. Otherwise, when we are tensile load is applied, it is expanded. So what happens there? The strain gauge out of the resistance, it expands or compresses when the load is applied. Until then it resists. Right? When it is resistance changes occurs, that proportional to the force applied. That is what I have written here. Change in the resistance is a measure of force applied. So for a graph, for an idea, a force applied, a compression or tension load that we are giving, force applied belongs to maybe compression, belongs to maybe tension, that forms the change in the resistance of the strain gauge that is measured through the electrical form of Wheatstone bridge. So that is what the idea here, a load applied, and then we can able to measure various resistance categories. At various places we are keeping and we are determining. A cylindrical tube, what I told you, a cylindrical tube to which strain gauge have been attached. The strain gauge have been attached. What happens when a forces are applied? When a force is applied, when the force is applied to the cylindrical cylinder to compress it, or otherwise a tension forces applied. The strain gauge gives a resistance. Strain gauge gives the resistance change, which is the measure of the strain. So that is all. And hence the applied forces measured, the force sensors we can use as a force sensor. What force or load is applied, we are finding through the strain gauge load sets. Nothing more differences are here. Next we come to the topic of pressure sensor. So we have seen the displacement, we have seen the movement velocities, we have seen the force applied. Now we are going to see about the pressure or maybe a fluid pressure applied. How to determine those things. See, a chemical, petroleum, or power industries are often in need of monitor the fluid process. See these examples, the chemical industries, fluid flows, petroleum industries, petrol, oil, gases, fluid flows, the power industries, the turbine, everything flows. We have to measure how much it is. Therefore, we want to maintain a pressure for the safety purposes, or how much it is we want to measure. Those things. The fluid pressure can be measured by using by elastic deformation principle. So the fluid pressure can be measured by the elastic deformation principle. What we are using here principally, we may use the rubbers or tubes or pipes in such a way that the fluid or liquid goes inside. Under this tubes or rubbers, changes are elongated. Those elastic deformation you are going to measure as a pressure change. Right? That we are going to measure as the pressure change. So what are they available here? So for example, we have taken 3 conditions here of number 1, a Bourdon tube, where we will have a tube in format of circular, where we are going to apply the pressure here. We call this as a C tube. We call this as a C tube, where when the pressure applied, it expands. It expands here. It expands here. So with respect to that, we will find it. Nothing but a fluid pressure applied over the tube. Diaphragm, what we are doing here, we have a box and the inlet is coming here, and a rubber of diaphragm material we have kept here and closed format. When this pressure load is hitted here, when the pressure load is hitted, this diaphragm rubber out of resistance, it expands or elastic deformation occurs. So that deformation is measured. So obviously this capsules and bellows in the same similar format, it is in the format of capsules. It also absorbs. So here we have an inlet. Accordingly it comes in, it expands, it goes out, it contracts. This elastic deformation we are going to find. Okay. So therefore, how we can do this here in the first options? I have taken a first option of this Bourdon tube. So I have taken this Bourdon tube and we have to see. So number 1, the first one, the fluid pressure sensor, the sketch. When a tube is in the form of a C-shaped tube, when the tube is in the form of a C-shaped tubes, it's being generally known as a C-type Bourdon tube. We know this now. It is in the format of C. It is in the format of C. It is in the format of C. And we are going to apply the pressure here. See, the pressure comes here. Pressure comes here, we are applying, and it goes to the tube. And this end of the tube are connected to the link mechanism to the pointer. So when the liquid flows inside, you can tell like this. When the liquid flows in such a format of, if the liquid flows here like this, what happens? It makes elaborating of these things here and there. Elaborating of this link. So this movement makes a change in the indicator's scale. So these indications can be founded as a pressure gauge or pressure bar, millibars, whatever it is, a pressure measurements. Okay, so this C opens up. This C opens up to the some extent when the pressure in the tube, increases. For our understanding, I have added here a small animated. See, we have applied here a pressure, and what happens? It goes inside. With respect to that, the link mechanism connected, the pointer moves up and down. So maybe a 30 bar, maybe a 40 bar, maybe a 10 bar, whatever it is, we are identifying a Bourdon tube pressure gauge. We are using this. A simple mechanism to measure the pressure gauge. Next, as the second one, we are coming here as a fluid measurement sensor, as a diaphragm. As discussed earlier, this belongs to the pressure gauge. A diaphragm doped with a strain gauge are generally used in the measurement of inlet pressure. So what we are doing, The diaphragm, we are using a rubber component. A rubber component we are using. But also, diaphragm rubber component, elastic deformation occurs. But the measurement system, for the closed loop, for the measurement system, we are adding the strain gauge here. Additional. When the change in the diaphragm happens, that the change of displacement or the pressure applied is converted into electrical format through the strain gauge. The methodology, we are using elastic deformation of the rubber, and over the rubber for the conversions for the measurement of the change, we are using the strain gauge here. A simple mechanism, we are applying a pressure here, a fluid pressure. It comes and fills, and therefore it gives a load pressure here. It will gives the pressure here. So therefore the elastic deformation here and there it occurs. Here and there the changes occurs. This changes we are going to measure through the strain gauge measurement. A typical arrangement of strain gauge on the diaphragm is shown. Right? A typical arrangement, the strain gauge is fixed, that is showing here. So the material we are using, what we are using here? So the material we are using is a rubber as a diaphragm. The application of pressurized fluid displaces on the diaphragm. The change in displacement occurs there. This displacement measured by the strain gauge again. Very simple mechanism. We have seen a Bourdon tube where the C-shaped it changes and the pointer measures. And the diaphragm where the same pressure applied, the diaphragm, the displacement, elastic deformation occurs. This deformation are measured to the strain gauge electrical resistance format. Two-way we have them. Right. Here, I want to play a video clip here for comparison of this diaphragm and Bourdon tube. You see, I have compared here this two Bourdons and diaphragms. These two works on a different principles. One is based upon the C-tube of a C-tube comparisons, and one is based upon the diaphragm of the change in the rubber. So these mechanisms are used here at the based upon C-tubes and the Bourdon tubes, C-tubes and diaphragms. So here we are using the link in the Bourdon tubes. We have used the link of mechanism according to the inlet pressure. It changes. Usually by the standards we are using this, but here there is one small problem is there. High pressure cannot be measured. The low pressure, overload conditions and critical media cannot be measured. What is low pressure? What is low pressure? Here in diaphragm we have up to small millibar you can able to measure. Small millibar, but there we have a small condition of a bar, minimum of 1 bar is starting. Here it is minimum 16 bar we can measure. Here what happens therefore, when the diaphragm liquid goes inside, here also the link mechanism operated. But what happens, here the minimum of 0.01 bar is not possible, but here the minimum of 0 bar or less than 16 millibar is measured. That is our low pressure. And overload condition also can be possible. When the 5x times, multiple times, 10 times, 40 bars, when the overload it exceeds, it shows. Right? Therefore, we can able to use the overload conditions, minimum low bars, or any critical media, whatever the fluid is, maybe a water, maybe petrol, right? Maybe a gas, whatever it is, the fluids, whatever items we can, the critical various media is nothing but any fluids, the water, oils, petrol, diesel, any media we can use there. So that is what, any aggressive media conditions we can able to use in these situations of diaphragms. Therefore, we are using this diaphragms better than that of this diaphragms, better than that of this Bourdon tube. But by the standard as we are using this Bourdon tube, but even though diaphragms are recommended here, the industrial standards if recommended. But here in the diaphragms, the low pressure, overload conditions, critical medias, anything else we can able to do in such cases. such cases. So that is all. Right? Okay, from the video you will see to the next one. So the next one we are taking here as a capsule, the third one. The third one. How it is there? It is formed by the combining two connected diaphragms. So here we have taken about one diaphragm we have taken. So this is one diaphragm. Already we have kept, and the force applied here, and we have connected now the two diaphragms in such a way we can able to take into two pictures, which is converted as a capsule, a closed capsules. It has enhanced sensitivity. It has enhanced sensitivity in the comparison with that of diaphragms. As because we can able to low pressure also we can able to measure here. A minute changes also we can able to measure here in the capsules. The diaphragms or multiple diaphragms are added to measure the low pressures also. The capsule consists of two circular wound membranes. The two circular wound, that is what we have told you, 1 and 2. Okay, two circular wound membranes and tightly sealed part. Tightly it is sealed. So we can tell some of this is nothing but a below here, but the next one we are going to see. But even though here one capsule is there, 1, 2, all together is called as a stack of capsules. A stack of capsules, capsules are called as bellows. So these capsules are attached to the converted to the bellows, and similar patterns we are going to use for the measurement of fluid pressure. Okay, the capsule we are applying load, the change occurs, and we can measure to the strain gauges. Right, see the bellows we can tell us a 3B and 3A. Right, likewise, okay. A stack of capsule is called as a bellows. A stack of capsules is nothing but 1. You see, this is 1, this is 2, this is 3. It continues to maintain, to get the low pressures. Identify the low pressure measurements. It consists of several capsules to form a one bellow. Applications what we can have here for the measurement of the compressed air systems. So compressed air, it goes in. Again I am repeating the same, but the format is different. First we have seen the strain load cells for the force measurements. Then we are seeing about the fluid pressure measurements like diaphragms, capsules, bellows, Bourdon tubes, all where the air is going in, the pressure is going in, the fluid pressure is making the changes. Those change resistance of the material varies. Here it enlarges. The elastic deformation occurs on the capsules and bellows. So those things connected to the pointer, those pointer deviates from its calibrated position. Those things will be as a measurement of pressure. So compressed air systems, pumping of fluid and water, air, anything, pumping systems we can use. Let's see, this is what the image of a bellow. We have connected various capsules here, and this is connected to the pointer for the 0th position. When there is an inlet here, P1 diverts from the calibrated scale. When the inlet pressure 2, it deviates here and there from the calibrated. It should be maintained at the calibrated position. For its maintenance, the fluid pressures are changes here and there, or otherwise when the pressure comes in, the deviations are measured from the calibrated to make it again to the stable position. So likewise we can able to do. I would like to play a small video clip here for our understandings. See, what we can do here, we have connected a Bourdon clip to the top and bottom. See, when there is a pressure here at the top, the below air or fluid fills from the top, and therefore the pointer which is connected to the bellow, which comes down in such a way we can able to measure the deviations. We are applying pressure or fluid here, it comes down, it operates through the bellow to the pointer, and the pointer deviates, and we are measuring here. A very simple mechanism, no such electronics, nothing else is there. A simple mechanism of usage of a bellow for measurement of the pressure gauge. Okay, see, the changes occur very easily. When it released, when the pressure is released, it comes again to the normal position. When the pressure released, it comes to the normal positions. Right. Now, up to now, we have covered 3 categories of pressure gauges, such as Bourdon tube, next the diaphragms, then the capsules and the bellows, and see we have completed with some small clip also. Next, we are going for the other type of sensor. We naming those things as light sensors. We naming this as a light sensors. You see, it's a very simple mechanism. Light sensor is a device that is used to detect the light. When the light comes in, the sunlight comes like a solar. You can take as a solar cells. When the light absorbs and it regenerates. Likewise, there's some examples. It is other process we have to see. But as of now, it have a photoresistor in between. A photoresistor electrode is there, which is we call it as a semiconductor. Photoresistor. If sunlight absorbs, it loses its resistance. Initially, it will be like an insulator, which does not permit flow of electrons from here to. We have taken one electrode of cadmium sulfide electrode. We have taken. Let us consider. So now we have connected this part of 2 parts. We have connected these 2 parts. One direction, one conductive material, and in the another direction we have one more conductive material. We have 2 conductive materials in both ends, and we have connected this. We have connected this to the power connections. Okay, but the circuit flow will not happen. Circuit flow will not happen. Why? Because we have an insulator here. We have a solid insulator here, which does not permits the flow of electrons from here to here. It does not permits. Therefore, this is a photoresistor. This is the photoresistor. So what we are doing here, we are going to, it is having the capability when it is heated, it loses its property of a resistive property. That's why that we are using here. So this is the electrode we are having. So 2 conductive parts. So conducting resistance are there. Inside in the middle we have a cadmium sulfide electrode. When it is heated, we come with later here. See. So this is the example, a symbol of this photoresistor. We have this red color line belong to a resistor line. In between, in this one direction, in this one part we have one conductive material. In other part we have another conductive material. We can tell here like this. This is one conductive material, 2 conductive material, and divided by the photoresistors. See, so this is the diagram what I mentioned there. Here we have one conductive material, and other side we have second conductive material. In between we have a photoresistor, this plate, this like this it is there. Okay, some photoresistor are available. It is the actual photoresistor which are using in the industries. Okay, and when the photoresistor is also known as a light dependent resistor. It is also known as the light dependent material, as because it's when the light falls down, it loses its resistivity. Therefore, it is a light dependent material. It has a resistor. This resistance decreases, the main point. This resistance decreases with increasing in the incident light. When the light increases, resistance decreases. Therefore, conductivity done. So when there is a resistance are removed, what happens? The circuit is closed. So we can tell when the resistance is removed, the circuit is closed here. So the flow occurs. When we are connecting a bulb here, it will flow, it will blink. Okay, we understand this. Okay, it is made up of high resistance semiconductor material of which one? A cadmium sulfide electrode that we have seen there. The resistance of the cadmium sulfide photoresistor varies inversely to the amount of light incident. What is inverse? This is the inverse. This is the inversely proportional. Light increases, resistance decreases. This point you have to add there. So this point we understand. A resistor, two conductors. This resistor is a cadmium sulfide. When the light falls, it loses its property. Therefore, conducting occurs. And then when the light falls, it can be used as a switch. When the light falls, switch to be off, like a street lights we can use. When the sunlight comes, automatically street lights to be off. It's an example of street light photoresistor. We can use photoresistor as a street application in the street light. So this is the active skin. So the cadmium sulfide resistor coil is mounted on a ceramic substrate. That is okay. We are pasting and keeping. This assembly is encapsulated in the resin materials. The sensitive coil electrodes are connected to the control systems. Through the lead wires. We are connecting here. We are taking out those connecting materials. We have seen this connections. They are talking about these connections. Okay. So for the idea, we have mentioned the same image also here. So this is what in close you can see. This is what the resistor, the original one, which have the two wires. This one and this one. Two wires and one electrode. Resistive photoresistor electrode. Cadmium sulfide electrode. So I want to represent the same in the graphical format. See, here we have the resistance we have measured in the ohms. And it is in the illuminations of light fall. Here we have the dark time. At the dark day, at night time, when the street light is in the active, there is no sun rays or no brightness are there. So the resistance is high. Okay, so this we can use as a switch. And when it happens, what happens there? When the sunlight arises, what happens? It decreases. The resistance decreases. So the conductivity again comes. We can store those things in the solar cell as a battery also. Conductivity comes, we are storing in the battery. Conductivity goes, we are replacing those batteries with the power supply again later. That are other circuits are there for that. So the resistance decreases. The resistance decreases as the light source increases. So this is what. So for identification, for the symbol, we have a small photoresistor at the middle, and the two sides we have a conductive material 1 and conductive material 2, and those to be connected to the circuit. Here also, for this photoresistor, I want to play a small video clip here. See, I have taken a voltmeter in which I am connecting those photoresistor wire. I am connecting this photoresistor wire in the two ends, and it is ready. The resistance is measured in ohms. There are volts, right? We are measuring in ohms. Therefore, I am changing this voltmeter position to the 20 kilowatt of or 200 kilowatt of ohms, because that is a maximum. Okay, so that I have changed now, and I have connected those two clip of photoresistors into the voltmeter. Now what happens? When the sunlight rays are fallen, I am using the phone to make it. When the light rays are fallen over the resistor, it becomes less in the resistance, the electrode and the conductivity is there. Therefore, what happens there? You see, when it happens, the voltmeter reduces. It reduces, resistance reduces. The light increases, the resistance reduces. When there is no, it becomes full. You see, when there is no, it is showing a full volts, full resistance of ohms. When the same light falls there, the resistance reduces. It not absorbing. And in such a way, we can able to understand this photoresistors. The applications of photoresistors in computers and wireless phones and televisions to automatically measure, automatically control the brightness of the screen. Where they are using this in computers, wirelesses, phones, televisions, everywhere they are using. They are using like this the phone. There also one photoresistor they are using maybe. Right? When the sunlight falls, automatic control of screen. This one they are using inside photoresistors. Automatic screen control, brightness controls are available. Then it is when it is terminating, disconnecting, which is used as a switch. Automatic street lights. This is what example we have taken. Automatic street lights, on-off switches, like the on-off switches in spaces in robotics where we are using to control and guide the motion of the vehicles, in the robotic formats. The light sensors enables the robot to detect light. Very important. We have seen when the light reduces, light increases, resistance reduces. The same can be used to detect the light, whether it's available or not, for the door opening or not. Likewise, when an object moves inside, when the sun spots, the light increases or decreases, the robot detects automatically. So these sensors we can use there. Robots can be programmed to have a specific reactions for a certain amount of light is detected. When the light is detected, it has a specific task. We are interlinking, multidisciplinary tasks we are doing, a sequential controls, a closed loop, something. When the light is detected, this specific program, a set program to be run. So likewise we can able to do. Automatic flashlight in the cameras. So this is everywhere in iPhones and the smartphones, Samsungs we are using. At the day, the flashes. At night, the flashes. When we have to open the flash, when we should not open the automatic flash screens. Those all depend upon this photoresistance elements. So we have to understand those things also. So in this session, what we have covered, the summary of this class, we have seen about the types of sensors. We have seen about the types of sensors. In this today's class, we have seen about a force sensor, such as a strain gauge, right? And then also we have seen about the pressure sensors, in this we have seen the Bourdon tube, and then the diaphragm, and then the bellows. Right? Additionally, we have seen the third one, as we can write it here itself. Additionally, we have seen about the light sensors. Light sensor of photoresistor. all are very important for the study purpose. Anyway, any questions will be asked. The remaining part of the types of sensors, we'll see you in the next session. Thank you.